The hack computer is a 16-bit machine. So the computer is made up of the CPU, the instruction memory, also called the ROM, and the data memory, the RAM. Now it's essentially as a Harvard architecture, which means there's different buses for the data and instructions. Now both memories are 16 bits wide with a 15-bit address space. And there's also two memory mapped I/O devices, a screen and a keyboard. Now in addition, there's also two 16-bit registers. The A register, which is used to store both addresses and data, and the D register, which is data only. So this is a simplified architecture of the hack computer. So actually these bits here, these are what make up the CPU. So the grey, the area inside the grey is inside of the CPU. So we've got the ALU, the D and A register, program counter. There's also a decoder. This is not exactly a chip part that you'll build, but it's more the kind of you see it's various bits of combination of logic what's used to kind of decode the instructions. And then external to the CPU we've got the ROM. So these are where the instructions are stored. So the instructions get fed into the instruction decoder. Which instruction we're up to determines on the program counter. So we've seen before the program counter essentially stores the address of which instruction to fetch next. The RAM stores the data only. So these are the three parts essentially of the computer. So this is the CPU, the ROM and the RAM. So there's two registers in the hack computer, A and D, and the computer can also access data stored in RAM. So this is not a load store architecture, because it can also get data stored in RAM. Now, the RAM address that we'll access is always the current value of A. So the A register stores the address which you want to access in RAM. So we're going to write that down with the syntax memory and square brackets A. So the contents of the A register are the address of the data we want to read from RAM. Or when we have to do the hack machine language, you'll see we can just use M for short. So M is just a shortcut to access a memory location specified by A. So it actually takes two instructions to access M. So firstly, we need to set A. So whichever address we want to read from, we write that value to A. So we want to read from address 99, we'd set the A register to have a value of 99. And then we can read or write to or from RAM by using this M instruction. So first set A to the required address, then interact with the RAM. So we look more closer now at this architecture. You can see the ALU is actually, always one ALU operation is done on the D register. So this is using the D command. So you write D, it means you access, you're using the D register. And then the other input to the ALU is always A or M. So depending on the status of this multiplexer, either the A register will be fed into the ALU or the memory address. Now if we are reading data from memory, remember that the address is stored in the A register, and then when we read from RAM, whichever address is stored in there, that's the slot that would read from. So just to summarise, the ALU, it always does an operation on D, and then depending on how this mux is configured, the other one will either be A or M. So we'll look how we can use a D register. So D is purely used to store data values. It's essentially numbers. We don't store addresses in there or anything. We just store data values. So we can set the value of D directly to 0, 1 or -1 using arithmetic logic unit operations. Remember, when you built the ALU, there's certain operations to create 0, 1 or -1 on the output. So we can use these operations to set the value of D. So for example, you can do D equals 1 and it'll set the value of the D register to 1. You can do D is 0 or D is -1. So these are the only literals you can set directly in the D register. So for example, you cannot do D equals 67 is not a valid instruction. 67 wasn't one of the ALU operations. So if you want to set a literal value in the D, you have to essentially load those values from M or A. So for example, you could put the value 67 in A, and then you could set D to be the value of the A register. So the only ones you can set directly in D are 0, 1 and -1. So A register is a bit more flexible. So it's got 3 uses essentially. So number 1, it allows us to access the data memory, so the RAM, by storing the address which M refers to. So remember, A, we can use it to set the address of RAM. We can also use it to store data. So it's not just addresses, we can also store data. And it's actually, we can store any literal value essentially in A, and it's actually the only way to load a literal value into our program is by first loading A with that value. And then it also allows us to access the instruction memory or ROM. So again, in this, when it's used to access the memory, the A register stores the address, and then whenever a jump command is executed, whichever instruction is at that address will be fetched in the next cycle. So it allows us to access RAM by specifying the address, access the instruction ROM by specifying the address, and also by loading literal values in. So it's got uses for addresses and data. So the instruction, we have to look at the kind of zeros and ones format, so the binary format of the instruction. We can see, because the register is 16 bits, and the first bit here, so bit 15 is a 0, it tells us that's an A instruction, and then the other 15 bits then we use to set, we can set any 15-bit value, and we do that using this at syntax. So if you wanted to load the value 15 into the A register, you would do at 15 in your code, and that will load the A register with the value 15. So just remember about this at assignment. So you cannot, this is not valid syntax. You can't do A equals 15. You cannot assign the value 15 to A. You have to use this at 15 syntax. So whichever number you've got here, obviously assuming that it's no bigger than 15 bits, will be loaded into the A register. So that's the A instruction. Now this, what we call a C instruction, this is essentially a computation that's carried out. So this is a real workhorse of the hack computer. This handles all the computations that are carried out by the computer. So it's actually made up of 3 possible parts. So the kind of full form of a C instruction with this, we'll have a destination where we'll do a computation. We'll store the results of the computation in the destination. Then there may be a jump. So we've always got to do a computation. You can see in each of these 3 options, we've always got to do a computation. But we can see at the destination, the jump are optional. So you may want to do a computation, store it in the destination, and then jump. In that case, you would use this format for the instruction. You might want to do a computation and then jump without storing the result of the computation. Or you may as well you might want to just do a computation and store the result in the destination and not do any jump. So these are the three different formats of the C instruction, and that's essentially all there is to it. We've got our A instructions and our C instructions. So this is a format for a C instruction, so it's a bit more complicated than an A instruction. So we can see now this bit 15. So when bit 15 was a 0, we knew it was a C instruction. When bit 15 is a 1, we know that we're referring to a C instruction. 14 and 13 are not used. These are just set to 1. And then this A bit is used to select between A and M. So we saw before with the ALU, we always did an operation on the D register, and then the other one we could select between A and M. So this A bit is used essentially to select between A and M. Then we've got our 6 computational bits. These select which computation to carry out, and these are essentially the ALU opcodes which we've seen. And we've got 3 destination bits. So these are used to set the destination where we want to store the result, because the ALU is going to do some operation and then it'll output a result. So then that result we can either store it in A, D or M, or a combination of those 3. And the final 3 bits specify a jump condition. So once we've done this computation, we might want to jump to a different instruction. Rather than just doing the next instruction, we might want to jump to a different instruction in the ROM. So first look at the computation bit. So these are the 6, as I said from the ALU, the 6 computation bits are exactly the same as the instruction bits of the ALU. So these are the 6 C bits, and these, using these gives us 28 different instructions in our instruction set. So they're summarised in this table here. So when we did the ALU, these are the kind of different, these are the 28 different operations. So these are the different operations that we had. But now, when we're actually doing with the computation, because we can select between A and M, it gives us slightly different variants for this. So for example, when we did the Y operation, using just the ALU on its own, this is where we just put whatever value was on the input Y, we put on the output. Because we can actually select between A and M, it gives us 2 different instructions for this. So depending on the value of A, we'll either have A and M. You can see this is repeated throughout. So all the instructions, essentially in the ALU, what have Y appears in. You can see there's 2 different variants. So depending on the value of A, or this lowercase a, we'll either use the A register or RAM. So essentially, there's 2 copies of each of those instructions. So the destination, so these bits control essentially where the output of the ALU is connected to. So the result of the computation essentially comes out of the ALU, and then that's fed into one of 3 locations depending on these D bits. So we can either store the results in memory, so we can write the result directly to RAM. We can write it to the D register, and we can also write it to the A register. And again, we can also do it to a combination. So you could, using MD, using the MD command, you could do an operation on the ALU, and you could store the results in RAM and in the D register at the same time. So you can see these destinations correspond directly to the bits. So D3, you can see from here. So D3 essentially controls M, D2 controls D, and D1 controls A. So for example, if all these 3 bits are 1, we'll store the results in A, M and D. So the jump bits tell the CPU what to do next. So typically they'll just fetch the next instruction in their ROM. So this is when the program counter has got its increment it's in this increment kind of condition, the value in the program counter will just increment to the next one, just keep fetching the next instruction in the ROM. But if we've specified a jump condition as part of the C instruction, then the program counter will be loaded with a new value which corresponds to a new address in ROM if certain conditions are met. So whatever value is currently stored in A, this is essentially the value what we're loaded into program counter. This is the address we want to jump to. It's whichever value is stored in A. So that means if you want to do a jump condition, you first must load this address into A using an instruction, A instruction, before doing the C instruction. So if you want to do a jump, step 1 or instruction 1 is to load the address to jump to in the A register, and then do the C instruction with a jump specified. So you've got to load the value before doing that. And then whether this jump occurs or not depends on whether the output of the ALU meets the jump condition. So there's various conditions here, so these jump bits. So essentially, if J1 is 1, it means the output is less than 0, so the output is negative. If J2 is 1, means when the output is equal to 0. And then when J3, so when this third J bit is 1, means the output is positive. So we can do a combination of these before, and that gives us the different kind of relational operators we can do. So, well, first, if all three are 0, we're not going to do any jump. But then we can do jump if the output is greater than 0, jump if the output is equal to 0, jump if it's greater than or equal to 0, jump if less than 0, jump if it's not equal to 0, jump if it's less than or equal to 0, and also just unconditional jump. So if all three of those bits are 1, we'll just jump. No matter what happens, we'll just jump to a different instruction. So you can see on this table how the bits, essentially this J bit controls whether output is greater than 0, J2 if it's equal to 0, and then that's if it's less, J1 if it's less than the 0. So now we know about the different computations, the destinations and the jump. We can look again at the hack computer architecture. So we know this is what we saw before. So ALU is always done, it always acts on D, and then the Y input. So this is when we built the ALU, that's essentially X, and this is Y. So the other input, the Y input, will either A or M, depending on this value of the A bit. So the A bit essentially controls the multiplexer and decides whether A register goes to the ALU or whether we read from memory. And if we do read from memory, remember that the A register, that sets the address. The decoder, this essentially gets the C bits, the computation bits. So these are these instruction bits of the ALU. So with this decoder circuit, you look at the instructions and feed the bits into the ALU, so that will determine which computation to do. The destination, so depending on the destination, the output of the ALU can be fed into the D register, into the A register, or into RAM, depending on the destination bits. And if you are writing to RAM, remember that you need to set the address first in the A register. And finally, we've got the jump condition. So these actually come from the Z, from the 0 and negative flags of the ALU. So if those flags, by checking those flags with the 0 or 1, we can determine whether the number's greater than 0, less than 0, or equal to 0, and that essentially decides what happens next to the program counter. Because if it's just going through the program as normal, the program counter is just going to be going 0, 1, 2, 3, 4. We'll just keep fetching the next instruction in the ROM. But then if we want to do a jump, we might want to jump to a different instruction in memory, so we might want to execute instruction 0, 1, 2, then jump to instruction 5.